So hello and welcome back to what is going to be the third lecture of this series. And this lecture we are going to be first reviewing the mathematics of special relativity, and we shall be trying to put it in use to our discussions of electrodynamics. So in a sense, the goal of this section is going to be to view electromagnetism through the lens of this special theory of relativity. What we have already seen and what we will find as we go along is that we will find that observers in different frames will not agree on what they call the electric field or what they call the magnetic field. They'll observe also different charge densities and different currents, but all of them will agree that these equations, these quantities, are related by the same Maxwell's equations. So there is more to this. It's when we formulate this Maxwell's equations, which is manifest. Which has manifest in invariance under these say Lorentz transformations, we'll actually see their true beauty, and you know, the slightly sort of problematic or cumbersome equations and vector equations that we saw, these will be replaced by a much simpler looking set of equations, which is also much more elegant, if you wish. So first of all, we will start today with a recap of what we have done. So remember, so let's start with the recap. So this is a recap. Recap. So remember, if we have Lorentz transformations, so suppose you have two frames moving along the x-axis with respect to each other at a velocity v. So then what we will have is the Lorentz transformations between these two frames are given by x primed is equal to gamma into x minus beta ct. There is no change in the y prime and the z prime. And actually, let me try and fit this all into, well, anyway. And also ct primed is gamma into ct minus beta x, where gamma is given by, as you know, gamma is just 1 minus v squared over c squared minus half, and beta is v over c. So these are our Lorentz transformations, and if you remember, these can be written, can be expressed more compactly, or say in a more compact form by using four vectors. So we call x mu something which is ct x y z, and then what we find is that, so we have x prime mu, which is ct primed, x primed, y primed, z primed, and x prime mu is given by lambda mu nu x nu, where the sum over nu is implied, and lambda mu nu are what are Lorentz transformations. So for the example that we have upstairs, lambda mu nu is just given by, or let's just drop the indices. So lambda is a matrix which is given by gamma minus beta gamma minus beta gamma gamma and 1 0 0 1 and all zeros here. So this is the matrix gamma. So this is the form of this is lambda essentially. So the Lorentz transformation, which corresponds to a boost, along the x direction, is given by this form. We also saw that Lorentz transformations could be defined as something that kept the distance between two events the same. So the point essentially was that, when we had distance of x dot x, which was given by c squared t squared minus x squared minus y squared minus z squared, the norm of this vector stayed the same, and this could be this could be used to define. So Lorentz transformations could be defined as the transformations could be defined as transformations that kept this distance invariant, and this led to the definition of Lorentz transformations by this equation, where eta was this matrix which was 1 minus 1 minus 1. This was the defining equation of these transformations. So this was our definition of Lorentz transformations. And from this, we saw that there were 6 independent types. So 6 independent Lorentz transformations, which were 3 rotations plus 3 boosts in this 3 plus 1 dimensions. So this was, if you wish, a recap of what we had done earlier. So what we want to do now is build on this a little bit more, so that we can get to an understanding of what we saw in the last class, that there was this specific way of trying to see that what was an electric force in one reference frame became a magnetic force in another frame. And we sort of gave you a physical picture of why this is going to be the case through these Lorentz contractions. But the point is that instead of trying to go through these sort of involved, these sort of long drawn explanations of which frame is moving in which direction and where this Lorentz contraction will be of what form, we will see that there is, so if we just focus on the mathematics of special relativity, this is actually going to take care of all of that, and we don't have to think about frames moving this way or that way, and what is shorter and what is longer, and which time is dilated and which one is not. So the mathematics of these Lorentz transformations will take care of all of that. But for that, we need just a little bit more formalism, which we want to describe here. Okay, so we will start off today with the idea of something called a proper time. So this is the sort of end of the recap, if you wish. So let's start off with something called proper time today. Okay. So what is proper time? So proper time is, so suppose there is a particle which is at rest at the origin of a frame S prime. So particle, so let's say particle at rest at origin of frame S primed. So which is, so essentially at x primed equal to 0. So the interval between 2 points on the world line of this particle. So remember, as a particle moves along space-time, it follows a trajectory, and this particular trajectory is called the world line. So now what is going to happen is that in this particular frame, this, if you just look at the frame, so let's draw this. So if you, let's maybe draw it in something like this. So if you are here, so the particle is at So the particle is at x prime equal to 0, and what is going to happen is that this would mean that the particle's world line is just this black line. Okay, so this just goes forward. So this is the frame S primed. So this is the frame S prime. So the distance between any 2 points on this world line. So if you are here, if this is point 1, if this is 1, let's say P1, and this is P2. This is T prime. This is X prime. So the distance is going to be, so the particle is at rest. So it just so it just goes along, traveling along T prime. So what is going to happen is that this is just, so the distance is given by delta S squared is just C squared delta T prime squared, right? Now, as you can see, the invariant interval between 2 points on this world line is proportional to the time experienced by this particle. So we have seen that delta S is actually same in all frames. So this is going to be invariant. This is going to be true in all the frames. So this particular thing, so this is, so let me just write this down, invariant interval between 2 points on the world line is proportional to time experienced by particle in this frame. So this must be true. This is, so this particular thing must be true in all frames. So we will define this, the time experienced by the particle in this frame is going to be called the proper time. So proper time this is going to be delta tau, which is delta S by C. Okay. Proper time tau is going to be delta S by C. So the proper time is going to provide a way to parameterize the trajectory of a particle such that all inertial observers agree. Okay. So let me write the sentence down for you. Proper time provides a way to parameterize the trajectory of a particle such that all inertial observers agree. This is an important thing. So now suppose you are looking at the trajectory of a general particle. So and suppose you're viewing, so consider trajectory, consider a general particle in a frame. So this is an inertial frame S, which is not the rest frame. Okay. So the whirl line of this particle will be parameterized. Whirl line is parameterized by x of tau and t of tau. Okay. So now let's see what this is. So del tau, as you know, is ds by c by our previous expression. Now ds is what? So this is 1 over c, and ds, you remember, is going to be dt squared minus dx squared. Dt squared minus dx squared root. Let's just drop the y's and the z's for the moment. Okay. So what can we do? We can pull out a factor of dt, and we are going to pull in the factor of sorry. I should make sure that I have my factors right, which are not right here. So let me just put in my c squared factor here, which I missed earlier, and there's a 1 over c, and I take the c inside and I put the dt outside. So this is very clearly 1 minus 1 over c squared into dx dt squared. This is nothing but the velocity of the frame of the particle. So let's call that u. So dt, so d tau is dt into square root of 1 minus u squared by c squared. This, as you can see, is our old familiar factor, and this essentially means that dt by d tau is just given by gamma. Okay. So this is so what you see is that the proper time is related to the time experienced in any arbitrary frame by a factor of your usual factor, that is going to be gamma. Okay. So that's what. So this is essentially also the velocity of the frame S with respect to the rest frame. And so that is where so this is u. So the u is the velocity of the frame S with respect to the frame S primed. So dt d tau is gamma. So why did we go into all of this? Now you remember that x was so the four vector for position was just x was given by ct and x, right? So this was what the 4 vector was. Now, if you were to think about something like velocity, and for that, if you had used usual dt, I mean, if you had used dx dt, this would no longer transform properly as a 4 vector again, because of the fact that the t itself transforms under Lorentz transformations. But now what we have is that we have been able to find something which is invariant under all such, all frames, all inertial frames. So Lorentz transformations keeps the proper time the same. So this helps us in defining something which is going to be a 4 velocity. So let's see how you do that. So x, as you saw, was this. So let's parameterize this in terms of tau. So this is just going to be ct of tau and x of tau. So for a velocity is now going to be given by u, which is dx tau by d tau. This is going to be just c dt d tau and dx d tau. Okay. And if you pull this out, so u is going to be given by, so let's just pull out dt d tau. So this is going to be c by, so what happens is that if you pull out dt d tau, this just becomes dx dt. So this is nothing but u again, u vector, u3 vector. And the factor in front of it is, as we have seen, is just gamma. So it's c and u vector. So this is the for velocity. So what is going to happen now? So we have got something which we call a for velocity. This is u. So what is nice about u? The thing that is nice about u is, so if there is an observer in a frame S, and that observer measures a particle's for velocity as u. So observer in frame S measures a particle's for velocity as u. Then another observer in a frame S primed with x primed as lambda x will measure for velocity as u primed is lambda times u. Okay. This is because d tau is invariant, and if you had defined something like this is because d tau is invariant, and so if you had defined, if u equal to dx dt, see if you had defined some u tilde as this does not have this property. So this is not a 4 vector. So this is not a 4 vector. Okay. So so that's what it is. So under any 4 vector A will transform as A goes to A primed is equal to lambda times A, okay, under Lorentz transformations. All right, so this is a 4 vector. Similarly, another thing that is a 4 vector is momentum. So what we will not really go into this so much, but let me just show you that, so if you have momentum, so this is just P is m into u, and so P can be actually written as E over C into P3 vector, where E is given by m gamma c squared. So this is the energy of the particle. This is energy of the particle. And P is m gamma u is a 3 velocity, is 3 momentum. Okay, I'll try and give you guys some homework, which is, so this one again, so P also goes to lambda P under Lorentz transformations. I'll try and give you some homework which clarifies this a little bit more. So this was another thing that I wanted to show you, because this is going to be important, and so that's that. Now, before going on more, so what we are going to be doing is we want to clarify some other notation first. So so as we said, there was an x mu, which was ct and x vector. And what did we find? We wrote something like x dot x, which was given as which we wrote down, and this x dot x was c squared t squared minus x squared minus y squared minus z squared. What we did is we defined this as so let me just pull up my notes from a little earlier, which hopefully you guys also have. So let's just remind ourselves of this. So this was also given by, so we defined x dot x as something like x transpose eta x, which we wrote as x mu eta mu nu x nu. Okay, so x mu was this form. we're going to define something which is notionally x lower mu, and this is given by Ct and minus x vector, such that x mu is just c squared t squared minus x squared minus y squared minus z squared. In a sense, what we are doing is that we are calling this guy, the guy that we have here, we are just going to call this equal to some x mu. Okay. So what is happening is that you can lower the index of an upper indexed thing by acting with it with eta mu nu. So let me just write this down for you. This may be a little unclear at the moment, but just hold on with us. This is just notation. So x lower mu is eta mu nu x upper nu. So this, remember, there is a sum. So there is obviously a sum over nu's. So if you want to lower an index, so you act it with this eta. So eta, as you remember, is going to be 1 minus 1 minus 1 minus 1. As you can see, if you act eta with this x mu, you end up with something where the spatial vector will change its sign. So we denote it by something which is lower. Okay, so this is going to be, so anytime that you are going to x mu upstairs into x mu downstairs is going to give you something which is this invariant form. If we at some point of time in the future, if we get more time, I'll try and explain this a little bit more. So very much like this, if you can raise and lower these indices with an index with a mu nu which is downstairs. You can also define the inverse matrix for eta, which is eta mu nu upstairs, which is going to be given by the same form. And with that, you can actually raise indices as well. So this is going to be given by eta nu mu x mu. So this is something that you can do. So you have, all I can, so this essentially, so eta mu nu, say mu rho eta rho nu is going to be given by delta of mu nu. So these are inverses of one another. So this eta mu nu upstairs and eta mu nu downstairs are inverses of one another. If this is a little unclear, what I want you to take away from this is that there are two sorts of vectors, one with indices upstairs and one with indices downstairs. The thing that distinguishes these two is the spatial part, the spatial vector that you have, which is, associated with with this 4 vector, the 3 vector which is associated with the 4 vector, that will change sign. Okay, x mu nu upstairs has Ct and x mu nu downstairs has Ct and minus x. Similarly, u mu that we have just defined, u mu upstairs will have c and u with a gamma in front of it. U mu downstairs will similarly have gamma, c, and minus u downstairs. Okay, so this is the distinction between something which is an upstairs index and something which is a downstairs index. And I should also say that the way these things transform under Lorentz transformations will also be so something with an upstairs index. So let's call u with an upstairs index. Let's call this big U. and u with the downstairs index, let's call this u hat. So u hat, so u transforms under Lorentz transformations to u primed, which is lambda u, but u hat transforms to u hat primed, which is actually lambda inverse u hat. So this is under Lorentz transformations. Okay, this is something that you can work out. I will not go into this particular detail, but the reason that I have been harping on this is the fact that I would have to define something with a lower index. So there is going to be a notion of something which is a del mu. So del mu is going to be defined as del x mu. So you see this has a lower index, okay? So this has a lower index, and that is why I wanted to make the distinction. This is going to be defined as 1 over c del t and delta, okay? So that's what I had. This is the reason why I wanted to go on and give you an idea of what exactly an upstairs index and a downstairs index meant. So this is what we will call a 4 derivative. Okay, I understand that this particular thing, this has been a little bit of abstract mathematics, and but the fun of all of this is that once you keep track of the indices and how they transform, you do not need to put in explanations like you have been doing, like time dilation and length contraction and so on and so forth. If you are working with a theory that is consistent with special relativity, you have to. So all you need is to make sure that you are dealing with these objects that transform nicely. These, an n-indexed object is called tensor. This is something that we will not go into in much more detail. But if you just make sure that you deal with these objects that transform nicely and the indices match up on both sides of the equation, you can be assured of the fact that you have a theory which is consistent with the special theory of relativity. And all of those, very nice explanations, if you wish, you don't need to go into that anymore. Okay, so so now what we're going to do is just look at something very quickly. So let's look at something. So let's look at something that we have been looking. We have stressed on a little bit before, conserved currents. So what did we have? So we had rho of x and t, which was the charge density. And we had j of x and t, which was the current density. And we had an equation which was del rho del t plus del dot j is equal to 0. This was the continuity equation. Right? So now let's try and see. So this is already consistent with the special theory of relativity. So let's see how that's the case. So let's define something called J mu, which is rho c and j. Okay. So let's first, we have to sort of convince ourselves that this actually makes sense. So if we start by in a situation, so this is going to be, so if you start off with a place where you have a situation, for example, where there are only a static charge density, which is rho naught, and you do not have any j vector. Okay, so j mu is just rho naught and 0 in some and now if we look at a frame, so let's say in some frame, now look at a frame S primed, which is boosted by a velocity v. So j primed mu is going to be, so let's again, okay, this is going to be j lambda mu nu into j nu. So this is in some frame S, in a frame S prime, boosted by velocity v. Now what is going to happen? This is something that we've seen before. So there is going to be a change in the charge density, and there is going to be a change in the current as well. This is going to be given by lambda, rho prime is equal to gamma rho naught, and j prime will be given by minus gamma rho v. So this is because, so the first equation says that the different observers will see different charge densities. This is because, Lorentz contraction. So the volume will get squeezed because lengths parallel to the motion are going to undergo Lorentz contraction. So this is something that we have already seen. The second of the equation just says that so we will just have the fact. So this is just a relativistic extension of the formula J is equal to rho v, and so there is a sign because so if the velocity of the boosted observer is v, therefore the charge is moving at a relative velocity of minus v. So this is what is going to happen. This is the transformation. So let's put a vector sign here as well. Now in the relativistic form, what is going to happen is that this equation above is going to take a very nice form. So we can just write this as del mu j mu equal to 0, right? So del mu j mu is equal to 0, and the reason that this particular thing, so this is just, we have just defined the del mu downstairs as above, and you see that this particular equation just reduces. So this is the relativistic version of the continuation equation. Notice that the indices are upstairs and downstairs, they are the same index. So there is going to be, so there is no leftover index. So this is one up and one down. So these are contracted, if you wish, in the right way. So it's very similar to what you had. So remember that, if you had x mu downstairs and x mu upstairs, this was something which was invariant. Similarly, anything which has, an a mu downstairs with a b mu upstairs, anything like this is a Lorentz invariant. You can actually explicitly try and do this, because what is going to happen is the index which has with the object which has an index downstairs is going to transform by the inverse of the matrix lambda, and the thing that has an index upstairs is going to transform as lambda. So lambda and minus lambda multiply each other and give you 1. So this particular thing is going to stay invariant. Okay, so this object that you have is going to be invariant under Lorentz transformations. Okay, so this is because of the thing that I just mentioned out here, that these two objects, so this is why this is the case. So this is true for any upper and lower indexed object. Okay, so this is, so again, what I will try and do is I'll try and give you some more examples, and we will try to make this a little clearer as we go ahead. But the thing that I want to sort of what we would be trying to do in the next lecture is that we will try and focus on now. So now that we have been able to figure out some form of how these the mathematics of special relativity, how it works, we will try and apply this to the our electromagnetic theory, and write down equations which transform nicely under Lorentz transformations. We will see how how you can read off the transformation of the electric field and the magnetic field from there. And we will also see how this Lorentz transformation actually mixes them up. Okay. So this is going to be something that we will be dealing with in the next lecture. And so before I end today, let me just take you through what we have done in the lecture today. I understand this has been a little, abstract, but let me just quickly go through this once again before I end. So we started off by just recapping what Lorentz transformations were. These were transformations that took you from between two frames, S and S primed, and if S prime was boosted with a velocity v, the way that this worked was given by a transformation like the above here. Okay. So this is something that you know very well. What you may not know that well is the fact that this is again something that we did earlier, but this can be written in a more compact way by introducing four vectors. So what are four vectors? Four vectors are sort of the generalization of three vectors by adding another fourth component, CT, to it. So if you were looking at the position for vector, so that is x mu. This is given by CT and your usual x vector. So when you want to look at the transformation of x mu, now this is given by x mu prime is lambda mu nu x nu. So this lambda mu nu are the Lorentz transformations. If you wanted to link up this with this, so if you wanted to link these two guys up, then what you want to do is, so if you were to look at the specific case where we had a boosted, when we had a boost along the x-axis, so this is going to be the form of lambda that you would want to write down. Okay, so this is something that should be familiar from last time around. And now I reminded you that an invariant that all observers, all inertial observers agreed on was the norm of this vector. So this was again from if you wish, rotational. We discussed before that similarly, if you had looked at rotations in 3 dimensions, this is also what you would have had there. You would have had x squared plus y squared plus z squared being invariant. What you have here is c squared t squared minus x squared minus y squared minus z squared being invariant. And this could be used to define Lorentz transformations, and this led to this, the form lambda transpose eta lambda is equal to eta. This is the equation that defines a Lorentz transformation, where eta is this 4x4 matrix with diagonal entries 1, minus 1, minus 1, minus 1. This led us previously to the fact that Lorentz transformations had 3 rotations, 6 independent sorts of Lorentz transformations were there in 3 plus 1 dimensions that were 3 rotations and 3 boosts. Okay. So that was a recap from the last time around. Now what we tried to do today, so the first thing that we tried to focus on was trying to define. So we had this position 4 vector. We want to define other 4 vectors like velocity and momentum and so on and so forth. For that, if we had just defined these by dx, where x was a 4 vector, by dt, this would not do, because dt itself, the time direction, as we saw, the time is different as felt by different observers, and this would not have been our proper way to try and write down a 4 vector, which is, a velocity 4 vector. So for that we needed something which was an invariant, and in order to do that we defined something called a proper time. So what was proper time? So we looked at the reference of we looked at the rest frame of a particle, and there we saw that the distance between 2 events on the whirl line of this particle was given by just s ds squared was c squared dt squared dt prime squared, sorry. So this, since ds squared is something that every observer agrees on, this has to be, so this notion, the dt prime squared, this has to be invariant for all frames. And hence we got to, so now we changed to, del tau, this was just notation, you could have just written dt prime squared as well. So the proper time tau was given by delta S by C. So this, remember, is the time experienced by the particle in its own rest frame. Okay. So that was that. So proper time, as we said, is it provides a way to parameterize the trajectory of a particle such that all inertial observers will agree. Now let's look at another frame S, which is moving with a speed u with respect to S primed. And what we are going to do is we're going to parameterize the x and t coordinates in the frame S by our proper time tau. So proper time, so del tau is given by ds by c, and ds is just square root of c squared dt squared minus dx squared. We have just dropped y's and z's. You could write them down if you wish. And what we find is that, so we just, So we find that, dt and d tau are related by a factor of, gamma again. So that was very useful. Now we have a relation between the time experienced at a frame S and the proper time that's given by gamma. Now what we can do is we can write down a velocity 4 vector, which is going to be dx. So this is going to be u is equal to dx by d tau. So this is c dt d tau by dx d tau. So u is given by, this expression here. So it's gamma c and u vector. Okay, so this now transforms in the right way, and what we find is, so if there is an observer in a frame S which measures the velocity of a particle as u, and there is another observer in a frame S prime such that x prime is lambda x, so that observer is going to measure u as lambda u. Okay. Now we don't have to take care, so since we have defined things in this nice way, now these transform in the usual way, and we don't need to think of transforming x's and t's separately. We have defined things in a nice way, so it transforms nicely under these Lorentz transformations. Similarly, as I said, any 4 vector is going to transform this way under Lorentz transformations. Another example of a 4 vector is the for momentum p. All right, so now the other thing, this probably was the place that a lot of you may have been very confused, but let me try and just go through this in the next 2 or 3 minutes once more. So x mu, we had written a 4 vector x mu, and these mu took values 0. So mu took values 0, 1, 2, 3. And this was, so mu equal to 0 was ct, and then it was x and y and z. X mu, so x mu 0 was ct, and x mu 1 was x mu 2 was y, x mu 3 was z. So we had found, we had sort of, we built the notion of x dot x, and this was given by this formula. Okay. Now what I try to say to you is that we will define something with an x mu, where mu, instead of being placed as an upstairs index, will be placed as a downstairs index. The distinction between x upstairs and x downstairs was the fact that x downstairs meant that the 3 vector that you have is going to change a sign. So there is a sign which has changed. So this is something which has changed, okay? So if you notice this and this, so there is a change in the sign here, okay? So why are we doing this? We are doing it in order to define, so we now are going to define x mu upstairs and x mu downstairs as something which is invariant. So c squared t squared minus x squared minus y squared minus z squared, the norm is going to be defined by x mu upstairs times x mu downstairs. Okay? So this means, so let's just try and work this out a bit. So let me just try and, okay. Okay, what? Yeah, so let me just put another page in between for you guys to see. So x mu upstairs and x mu downstairs is what? It's sum over mu equal to 0 to 3 x mu upstairs, x mu downstairs, which is what? X naught upstairs, x naught downstairs, plus x1 upstairs, x1 downstairs, plus x2 upstairs, x2 downstairs, plus x3 upstairs, x3 downstairs. So this is what? This is CT into CT, plus this is x into minus x, plus y into minus y, plus z into minus z. Right? Because x1 upstairs is plus x, x1 downstairs is minus x. So this is what? This is c squared t squared minus x squared minus y squared minus z squared. Okay? So this is invariant under Lorentz transformations. Okay? This is always going to happen with any two indexed objects. So if you have something like two vectors which are like this is always going to happen. Okay, let me try and explain that a little bit more. So we have defined x mu downstairs as this. So you can think of x mu downstairs as eta mu nu x nu upstairs. So let's try and understand why I say this. So x mu downstairs is eta mu nu into x mu upstairs. So let's try and understand this. This is what? This is 1 minus 1 minus 1 minus 1. And this guy was what? This guy was CT x y z. So you see that this is nothing but a changed sign. So CT minus x minus y minus z. Okay? Very simple. Now, if the second thing that I wanted, that I was trying to show you was eta. So if we had something which was upstairs, it can be multiplied with an eta mu nu which is upstairs and x mu which is downstairs. So let me try and show you this as well. So eta mu nu. Okay, so let's look at this. So eta inverse. What is eta inverse? Eta inverse is, say, let's define something called an eta hat, which is eta inverse. So eta hat into eta is equal to 1. Now eta is 1 minus 1 minus 1 minus 1. So this implies that eta hat is also going to be 1 minus 1 minus 1 minus 1. Okay, this is a diagonal matrix. This should be very clear to you. Okay. So what I'm going to do is that what I want to just show you is if you were to write this as the same thing. So if you were to write eta hat as eta upstairs mu nu, then eta upstairs mu nu and eta upstairs mu nu. So this particular relationship that you have out here just translates it to eta upstairs mu nu into eta nu some rho is just delta of mu into rho. Okay. Now this eta upstairs mu nu, if you again just write it in a form. So if you have something which is eta upstairs mu nu and x nu downstairs. So what is this? So this is again 1 minus 1 minus 1 minus 1 into CT and x, y, z, all with minus signs now. If you do this, this is just CT, x, y, z. So you see that this is x mu upstairs, as you saw before. It's very simple, but you need to just keep in mind all these indices going up and down, okay? All right. So that was the other thing that I had in mind. So as you saw, you would have indices which are upstairs, which meant that the 3 vector has a sign plus. This 3 vector will have a sign which is a plus. And similarly, if you have this downstairs, the sign here is going to flip, okay? So these are the ways that you are going to distinguish between an upstairs index and a downstairs index. You multiply it with this eta, and eta has these signs here. So what is going to happen is it's going to flip the sign of your 3 vector, okay? That is what is going on between upstairs indices and downstairs indices. Another thing that I want to emphasize this, I'll try and give you some homework and clarify this a little bit more, is that if you have any upstairs index, let's look at U. So we'll denote this as this matrix, if you wish, U, and the lower with this U hat. So under a Lorentz transformation, this is something that we have seen. A 4 vector actually goes to lambda times U. U prime is lambda times U. Now, if this had an index, so these had indices upstairs, this goes as this. If it had an index downstairs, it will actually go as inverse of U. So what this means is that if you have a certain, so let me try to clear this for you. So if there was a vector which had an index upstairs, so if there was an A mu which was like, so this we called an A, some A. So under Lorentz transformations, A goes to A primed, A goes to A primed, which is lambda times A. And there was a vector B mu, which an index B mu downstairs. So B, let's call that B hat. So B hat goes to B primed, B hat prime. This as we said had a transformation with an inverse. So A mu B mu, A mu upstairs at B mu downstairs is going to go to, so this is essentially equal to A dot B hat. This is going to go, so this, when you transform this, so this goes to A prime dot B hat primed. First one goes as lambda A primed, and the second one goes as lambda inverse B hat. So lambda and lambda inverse go off amongst themselves. So this becomes A primed. Sorry, too many primes. This is not a prime here. There's no prime here. So this is essentially, so the lambda and lambda inverse go among themselves. So this just becomes A B hat. So what you see is that this quantity is invariant. So this is invariant under Lorentz transformations. Okay, so this is another thing that I wanted to stress. Finally, we defined something which was a 4 vector. This had an index downstairs. And I showed you that if you write down the continuity equation in a 4 vector form, which was where you looked at J mu as rho C and J, in that case you could write down the continuity equation in a form which is del mu j mu equal to 0. By the argument that I've just given you, del mu j mu equal to 0 is going to be an invariant under Lorentz transformations, because del mu downstairs transforms as an inverse of lambda, and j mu upstairs transforms with a lambda. So this stays invariant under Lorentz transformations. So this just means that the continuity equation holds in this form in all reference frames. So I understand this may have been quite a bit involved. So I'm going to stop here for now, and we will take this on in the next class, and we hope to do some more. Thank you very much.